will continue looking at some examples in dimension homogeneity. The first problem is used for traffic engineer, and it's a model that's known as a stopping sight distance. This is used for traffic engineer, a sub-discipline in civil, to design roadways, and it's to help estimate this distance as when a driver needs to stop his car while traveling at a certain speed after detecting a hazard. So S is equal to V squared over 2G F plus minus G plus TV. S being distance, it's going to have a unit of foot. V is speed, foot per second, and G is going to be 32.2 foot per second square. And G, it is the coefficient of friction between the roadway and also the tires. G is going to, I think I'm already wrong. This is not G, this is F, okay? This G is a grade of the road, and a T is reaction time, so that's in second. So knowing that, we can go ahead and try to find F and G dimension. First of all, you notice this F and G, they are plus minus inside this parenthesis. In order to plus or minus, they have to have the same dimension. So F and G is going to be same dimension. Then you also look at this entire formula here. S is being the foot, right? That's side distance. And we have this first cluster plus the second cluster. They have to have the same dimension. And when they add up together, they are going to have the same dimension as this one as well. So they will share the same dimension as foot. So knowing that, so this problem could be simplified as this V squared 2G F plus minus G. That's going to have just a unit of foot, right? Now we can plug it in. V being velocity, foot per second, and it's square, and a 2 is a constant. We don't worry about the unit. G being 32.2 foot per second square, we don't worry about the number, only the dimensions. It's foot per second square. And F and G, it has the same dimensions, so I'm going to write like that. Then equals foot. Now let's see if we can cancel second square, they are at the bottom of the fraction. So then this basically becomes foot divided by FG dimension equals foot. So what does that tell us? This F and G sharing the same dimension will be dimensionless, because foot over something, no unit, is going to be equal to foot, right? So that's for this example. Now let's look at the second example. This is used in material science study. It's called annealing process. It's when we heat up a material at a certain high temperature and then let it cool down slowly to toughen them. And there's an equation to determine the temperature of that material. So it's T minus this environmental temperature, and then initial temperature of this substance minus the environmental temperature. All of that is going to be equal to AXP when it's exponential, negative 2H rho CL times T. Now let's go ahead and look at the units. So T, all this T gonna have a temperature unit, so it's degrees Celsius. H is going to be the heat transfer coefficient. And that is the unit we are solving. And rho being density. Density is kilogram over meter cube, mass over volume. And specific heat is going to be in the unit of joule per kilogram per Kelvin. Now, L is the thickness, so it's in unit of meter, and T is time in seconds. So now let's look at how we approach this problem. Then when you have T minus another temperature, then it's the same dimension. They're going to have the unit of degrees Celsius. Same thing for the bottom. That's going to have a unit of degrees Celsius. Then temperature over temperature, what do you think we're going to have the unit here? It's going to be no dimension, right? It's being called dimensionless. So if this is dimensionless, we know this is going to be dimensionless as well. Then exponent, which means it's E negative 2H rho CLT. If this whole thing is dimensionless, then we can again simplify this problem. We can say this exponent negative 2H rho CLT, this whole thing here is going to be dimensionless. So now let's go ahead and put our unit in. We don't worry about negative 2. It's a constant. H is what we are solving. T is the time, second. Rho being density, kilogram per meter cube. C, specific heat, that's joule per kilogram per Kelvin. And L, it's a thickness, so it's in meter. This whole thing is going to be no dimension. Let's see if we can cancel out some. Kilogram, kilogram cancel out. And a meter cube here become meter square. So what we have is H and joule divided by meter square. And I'm going to bring the second down here. So it's going to be 1/2. So this whole thing is dimensionless. Then we are solving this heat transfer coefficient. We know this is going to have a unit of joule per meter square per second. That's telling us how much heat is in joule unit, right? How much heat is transferred every second per cross-section area. Okay, so that's all for this video. I'll see you next time. Bye.